All right, so I just wanted to go over again why random assignment is so important. What random assignment does is whenever you have a treatment, so let's just say taking the online course versus not taking the SAT course in the classroom, random assignment allows us to take that online course and randomly assign it and give it to people that are in AP classes, not in AP classes, maybe like doing online learning, don't like online learning. So random assignment allows that treatment to go to so that everyone that's representative of the population will be able to sort of be part of that treatment. So it won't eliminate bias, so it won't completely eliminate bias. So it's basically like saying I'm not going to completely eliminate the fact that maybe all the AP students are going to do much better, but it will help to reduce it because in that group we will be looking at people that take AP courses, don't take AP courses, like online learning, don't like online learning, and we're looking at the overall results, not just that one specific group. So in an experiment, random assignment means that the experimental units are assigned to the treatments at random using some sort of chance process. So it's not just the people that really like online learning that are going to take the online SAT course. All right, so how exactly does random assignment help to reduce bias? So it ensures that our sample that we've already chosen or our experiment is a good representation of the population. So let's go back to the hormone pill for a minute. If we randomly assigned a group of women to take the hormone pill versus not take the hormone pill, it would ensure that women who are concerned about their health versus not concerned about their health were in both groups. That also means that taking the hormone pill versus not taking the hormone pill, women of all ages are going to be in both groups. So it gives us a good variety, a good representation of the population in both of my groups. The goal is to create groups of experimental units that are roughly equivalent at the beginning of the study. So what that means is when I do the treatment of the hormone pill versus the not hormone pill, when I say the groups are roughly equivalent, that means each of them contain women that are concerned about their health, not concerned about their health, women that exercise and don't exercise. Both of getting the hormone pill and not getting the hormone pill will have women with all those characteristics in both groups. So what this does is this balances the effects of the variables among the treatment groups. So that's just like saying that I'm getting both groups are varied in the same way. I'm never going to eliminate bias, but it's just going to help to reduce it because I'm looking at the overall effects of the hormone pill versus the not hormone pill on a variety of different women. All right, so I want you to think about this for a second. When you have an experiment, it's going to be very important that you can describe random assignment correctly. So you have to be able to state how you're going to randomly assign your experimental units or your subjects to their treatment groups. So let's take a look at this example that talks about caffeine affecting your pulse rate. Many students regularly consume caffeine to help them stay alert. So it seems plausible that taking caffeine might increase an individual's pulse rate. Okay, is this true? So we want to know if we take caffeine, is our pulse rate going to increase? One way to investigate this claim is to ask volunteers to measure their pulse rate, drink some cola with caffeine, measure their pulse rates after 10 minutes, and calculate the increase in pulse rate. So this is kind of like a before and after. Pulse rates before, drink some caffeine, pulse rates after. Let's say we have a class of 30 students who volunteer to be subjects in our caffeine experiment. We want to randomly assign 15 students to each of the two treatments. So we want 15 students to drink the cola and then 15 students I'm trying to think of what else we're doing. Maybe 15 students would actually drink a placebo, and we'll talk about that in a minute. So we're going to discuss how we can do this using 30 identical pieces of paper, that's throwing their names in a hat, using technology, and using a random integer table. Remember that when we're doing this, okay, remember that whenever you're describing random assignment, you have to be able to give your directions to anyone walking down the street, and they would be able to do your experiment and randomly assign it. So they have to be specific. So if you read it and you're like, wait a second, what do I do? Then you know you need to add something. Okay, so here's what you're going to do for the first one. So this is like the hat method we sort of talked about previously, all right, when we're choosing a sample. So it's sort of the same thing, only now instead of choosing a sample, we're assigning subjects to treatments groups. So let's say we take 30 identical pieces of paper, write A on 15 and B on the other 15. We're mixing them thoroughly in a hat. Notice the key words, identical piece of paper, mix them thoroughly, and have each student select a piece of paper. The students who received A are going to drink the cola, and each student who received B are going to drink the cola without caffeine. So we have two colas here. One is with caffeine and one is without caffeine. All right, so we're comparing what happens when we do that. Now, the next one would be numbering the students 0, 1 to 30. Notice how they're the same length. On your calculator, use random int 1 to 30 to select 15 different students. Make sure you state the word different or ignore repeats from 1 to 30. These students will drink the caffeine. Notice how you're stating the students that you choose will drink the caffeine. Make sure you also state what's going to happen to the other 15. The remaining 15 will drink the cola without caffeine. How do I do that on a random number table? Number the students 1 to 30. I use a line from the random integer table and read 2-digit numbers moving left to right. Very specific. The first 15 different, or make sure you state ignore repeats, numbers from 1 to 30 will identify the students who drink the cola with caffeine. And then make sure you also state what you're doing with the remaining 15 students. They're going to drink the cola without caffeine. All right, so keys when we're doing this, make sure you state the word random. Anyone should be able to follow your directions. The digits have to be the same length. Make sure you deal with repeated numbers. Are you going to include them or ignore them? And when we're assigning treatments, we're usually going to ignore repeated numbers. And then don't just state who is going in each group. You have to state 15 students go to cola with caffeine, 15 go with cola without caffeine. Don't just state assign the first 15 to one group and the second 15 to another group. Well, which 15 are going where? Be specific. All right. Now that we've talked about how we do the random assignment, what exactly does an experiment look like? What does the design of an experiment look like? In a completely randomized design, the treatments are assigned to the experimental units completely by chance. So basically what we have here is we have all of our experimental units that we've chosen, and then we're just taking those experimental units and randomly assigning them to the treatment groups. That's all we're doing, okay? Most experiments will include a control group. Basically what that is, that's an inactive treatment or an existing baseline treatment. So that was like just when we were taking a look at the online course, like just doing the online course and then looking at the results. We don't have anything to compare that to. So we need to have some sort of comparison. Experiments without comparison are not necessarily really effective. So that comparison group is really important. So number one, you want to make sure that you're going to include where the random assignment takes place. So we start out with our experimental units, all right? Then we're going to state, okay, random assignment, we're randomly assigning them to students that are drinking the cola with caffeine, students that are drinking it without caffeine. Now in this case, we want to include how many are going to be in each group. So you want these groups to be about equal, 15 in each group. And then at the end, you're going to say what treatment you're giving them, with caffeine, without caffeine, and then make sure you compare the results at the end. Now, don't just say compare results. What results are you going to compare? You're going to compare the pulse rates of those that got the caffeine versus those that did not get the caffeine. So don't just state compare results. You have to be specific. Randomized comparative experiments are designed to give good evidence that the differences in the treatment actually cause the differences in the response. So that's like basically saying we can now establish cause and effect. All right, does the online course actually work? Does caffeine actually increase your pulse rate? Now, there are 3 principles of experimental design that are really important. The first one is control. Now, control for lurking variables that might affect the response. That basically is saying, okay, so if we have students that are taking the online course and we know that we have 2 major groups of students that take AP classes and students that don't, we want to think about how can we control for that? Maybe putting them into one group isn't necessarily the right thing. How can we control for those differences? Random assignment takes impersonal chance to assign experimental units to treatments. So it's not like you saying to your friend or your friend choosing, oh, I want to drink Coke with caffeine in it and see what that happens. No, that's using chance to assign the experimental units to the treatments. This helps to create roughly equivalent groups of experimental units. So all that means is that your groups have equal sort of differences between them. So when we're talking about the caffeine, maybe that's making sure that both groups have both have some males and females, both have some people that are athletes and non-athletes, both have some people that drink caffeine a lot and don't drink caffeine a lot. That balances those groups out, and it helps balance the effects of the lurking variables, all right, because they're sort of in both groups. Now, replication doesn't mean I'm doing the experiment over and over again. All replication means is that I have enough experimental units in each group so that the differences can actually be seen, that they can be distinguished from chance between the two groups. So if you do an experiment with 5 people, like that might not, maybe it's just those specific people that are responding. We want to make sure we have enough so it's a good representation of the population. All right, so comparison, let's just take a look at the principles of experimental design and let's apply those to the hormone pill. When designing an experiment, we want to make sure that you have 2 or more treatments. One of them can be the control. So for example, in the hormone question, we can use those not getting the pill as the control and those not getting the pill as the control, and those getting the pill are the treatment group. That should say treatment group. Now, random assignment, just keep in mind that that never eliminates bias. It just helps to control for it. Control means, are you going to be able to control for all the confounding variables? Absolutely not, but you can try to control some things, okay? So for example, the SAT example makes sure that both groups get the same pre and post tests, all right? Both groups would want the same teacher, the same content, and the same length of instruction. Why? So less confounding takes place. So you want to think about what you can control with an experiment and actually control it. There's going to be stuff that you can't control for, so that's you, but you want to think about what you can control and what's actually important that you do control. And then the last thing is replication. So like I said, this doesn't mean you're doing the experiment over and over. It simply means there are enough subjects to validate the experiment. The more replication, the more balanced your treatment groups will be after random assignment. So basically, the more people in your study, the better representation is going to be of the population. Now, when creating an experiment, it will be more convincing if the groups are the same sizes. All right, so when you're doing SAT online versus in the classroom, if they both have 50 students in it, that's going to be more helpful than if one has 10 and one has 30. So you want to try to get them to be about the same size. All right, so go ahead and just read this for a second. So this is an example of a well-designed experiment. Okay, so this was a good, well-designed experiment. We had a lot of replication. All right, we had 21,996 male females. We had a control factor. There were we had the aspirin and the beta carotene. Okay, and we also had a placebo drug. So the placebo drug was our beta carotene drug, and a placebo drug just means it looks exactly as the same as the treatment, looks, tastes, everything exactly the same as the treatment. It just doesn't have the actual drug in it. All right, so we randomly assigned them, so there was random assignment between the two, the drug and the placebo. All right, so since we had the 3 important principles of experimental design, that means that we are able to state that there was a large enough difference to give good evidence that taking aspirin does actually reduce heart attacks. Okay? All right, so I briefly talked about the word placebo. What does that mean? So it's basically like a dummy pill or an inactive treatment that's indistinguishable from the real treatment. Now, obviously, like the aspirin and the beta carotene, like if you were giving them these 2 drugs that looked like this, that would not necessarily be good because they would be able to tell the difference. So when you have a placebo, you want them to look exactly the same so that the subjects don't know if they're getting the placebo or if they're getting the actual drug. All right, so we just talked about how the 3 principles of experimental design were in that study. They used a design that compared the active treatments to a placebo, so that was comparison. We randomly assigned the treatment groups. We controlled what we could, so they were the same gender and occupation, and they followed the same schedule of pill taking. So maybe different genders react differently, so that's why we kept it the same gender. And then replication, there were over 5,000 subjects per treatment group, so that means that there was a large enough number of subjects to help ensure that the difference in heart attacks was due to aspirin and not necessarily by chance alone.